So tired of confusing magnetic field calculations? So in this short video, we are not just learning, we are going to master the secrets of magnetic fields generated by current carrying conductors. Stick with me until the end and I guarantee you will be able to solve any question on this topic. Let's conquer JEE and NEET together. Subscribe for more. The countdown is relentless. Just 60 days left until JEE Mains. Stop for a moment and let me tell you the brutal, uncomfortable truth that every other mentor avoids. Right now, you're carrying baggage, those class 11 concepts you never truly mastered, those crucial topics you keep skipping over, and those formulas that dissolves the moment you walk into an exam hall. And in the back of your mind, a dangerous thought is forming. 60 days is enough time to fix all this. But the reality is, it's not. Not with random studying, not without a surgical focused plan. We don't just study for JEE, we master it. We have generated results 10 times better than the national average, propelling over 500 students to jump 80 plus marks in their last 60 days. How? They stopped trying to cover everything and focus only on high weightage topics. They cleared every doubt, they had a strategy into place, and that is what Last Lab Booster program does. Senior IIT faculty sit with you, develop 60 days roadmap. Expert teachers guide you. In one-on-one class daily, every doubt is cleared in 24 hours, not random preparation but strategic learning. Ashish, Ditya, Sarthak were all able to improve from 150 to 250 in a matter of 60 days. Real student, real result, 60 days. Time is less and our strokes are even more limited. The choice is simple: continue on your current path or unlock a proven strategy that delivers results. Don't let opportunities slip away. Click the link below to book your free personalized strategy session now. By February 1st, just 60 days from today, you could be celebrating a completely new level of success. Next step is yours. Make it count. Right, so let us start with the problem types. So the first problem can be based on the application, or you can not the application, the direct formula of Biot-Savart law. Now, what is Biot-Savart law? According to this, if there is a current carrying conductor which is having a current I, and if I take a small element which is having a length dl, then we'll define a physical quantity known as current element, which is defined as I times dl. And we want to find the magnetic field at a point P, and its position vector is R. So the magnetic field at P by this current element is defined as mu naught upon 4 pi I dl cross r vector divided by r cube, or we can write this as mu naught I dl cross r cap divided by 4 pi r square. So in the exam they can directly ask you this formula, and the direction of magnetic field will be along dl cross r vector, along dl cross r vector. Okay, so if this current element and if this r vector lies in this plane of the only, then we can say by using right hand curl rule, if you curl your fingers from dl vector to r vector, thumb is pointing into the plane, so that will give you the direction of the magnetic field at point P. So it will be into the plane in this case. So we can find the direction by using right hand curl rule. So that direction is very important. If there is a wire which is having a current in the upward direction, then by using the same logic, the magnetic field to the right of the wire will be into the plane, and the magnetic field to the left of the wire will be out of the plane. So this is the symbol we're going to use: cross for into the plane, dot for out of the plane. If the wire is horizontal, then below this the magnetic field will be into the plane, here it will be out of the plane. If the current is going in the downward direction, then to the right it will be out of the plane, and to the left it will be into the plane. Okay, so this nomenclature you can remember. Now let us see the next concept, which is based on the magnetic field produced by a moving charged particle. So we know that when a charged particle moves, it constitutes a current. So if it is it constitutes a current, then it can also produce magnetic field. So let us see. If there is a charged particle Q and it is moving with a velocity v, and we want to find the magnetic field at point P, and the position vector of point P from the charged particle is r, and this angle is theta. Then if you look at the Biot-Savart law formula, the ideal its unit is ampere times meter, right? So if I replace ideal with q times v, what is the unit of q times v? Q is charge, v is speed, velocity, that is meters per second. So this is again ampere meter. So what you have to do, you have to replace ideal with q times v in the Biot-Savart's formula. So you will get the magnetic field produced by a moving charged particle. So magnetic field will be given as mu naught upon 4 pi times q v cross r vector divided by r cube, or we can also write this as mu naught upon 4 pi q v cross r cap divided by r cube. Again, in this case, the direction will be along v cross r, right? If we have a negatively charged particle, then the direction will be minus of v cross r, right? So the question can be based on this the application of Biot-Savart law also. Right, so and one thing I forgot to mention, mu naught is the permeability of the medium, and it will be nothing but 4 pi into 10 raised to power minus 7 in SI unit. Okay, so this you have to remember. Now the next concept is finite wire, the magnetic field produced by the finite wire which is having current. So let us see. So there is a wire which is having a current I, and suppose we want to find the magnetic field at point P. Now what you can do, suppose this perpendicular distance is given to us, which is d. Now if I join the ends of the wire with point P, let us find this angle. So this angle is theta 1 and this angle will be theta 2. So the magnetic field will be mu naught I divided by 4 pi d, where d is the perpendicular distance of point P from the wire, times sine theta 1 plus sine theta 2, right? So this formula you can remember, or there is one more formula which you can remember for the same arrangement. If r1 is the position vector of P from the left end, from where the current is entering the wire, and r2 is the position vector of P from the right end, where the current is exiting. Now find the angle made by the current with R1 and R2. So this angle, let me call this as alpha 1 and this angle as alpha 2, right? So we can also write the same formula as mu naught I upon 4 pi d times cos alpha 1 minus cos alpha 2. But if you use this formula or this formula, you will get the same result. How to find the direction? So magnetic field at point P will be out of the plane, right? It will be out of the, you can use the same logic, right? Either you can use right hand curl rule or simply the cross product rule, right? So it comes out to be out of the plane at this particular point. Okay, right. So the next concept is the finite wire at its perpendicular bisector. So if we have a finite wire, and this is the perpendicular bisector, and we want to find the field at point P, and this wire has a current I. So this angle is theta, this angle is also theta. So in this case, theta 1 is equals to theta 2 equals to theta. So if you apply the same formula, it will be mu naught I upon 4 pi d, where d is the perpendicular distance of point P from the wire, times 2 times sine theta, or you can say it will be mu naught I upon okay, it is not visible, let me write it over here. So it will be mu naught I upon 2 pi d sine theta. So this formula you can remember. Let us see the application of that. A regular polygon of 6 sides is formed by bending a wire of length 4 pi meters. If an electric current of 4 pi root 3 ampere is flowing through the sides of the polygon, the magnetic field at the center of the polygon would be x times 10 raised to power minus 7 Tesla. The value of x is, so here we have given a regular hexagon, right? And it is having a current which is 4 pi root 3 ampere. Let us say this is the direction of the current. And we want to find the magnetic field at the center. Now if you consider any side, if I consider, let me call this as side number 1. Due to this side, the magnetic field at the center, by using right hand curl rule, it comes out to be into the plane. Similarly, if you consider the second side, due to this, the magnetic field is again into the plane. So if you take any side, the magnetic field will be into the plane. So all the fields are getting added up. So what we're going to do in such questions, first we'll find the magnetic field by one side, and then we'll multiply that magnetic field with the number of sides. So let us consider one side. Right, so if I join center with the vertices, then the distance of the center from the vertex is nothing but the length of the side of the polygon. Now what is the length? So the polygon is made with a wire of length 4 pi meters. So the length of one side, let me take side as A. So A will be 4 pi divided by number of sides. So this comes out to be 2 by 3 pi meters. So we got the length. Now what is the perpendicular distance of the center from one of the side? Now this, if you consider OAB, now this OAB triangle is a equilateral triangle, right? So we can say the perpendicular OM is nothing but root 3 by 2 times A. So let me take this as D. So D will be root 3 by 2 times A, which is 2 by 3 pi meters. So it comes out to be pi by root 3. Okay, so now it is the case of magnetic field at a perpendicular bisector. So this angle will be 30 degrees. So in this case theta will be 30. So what is the formula? That is mu naught I upon 2 pi d times sine theta. So theta is 30 degrees, I is 4 pi root 3 ampere, and d we have just calculated, it is pi by root 3. Let us put the values. And mu naught is 4 pi into 10 raised to power minus 7. Current is 4 pi root 3, and sine 30 is 1 by 2, and 2 pi d is pi by root 3. So this will become square. Let us simplify this. So this pi square will get cancelled out. This will get cancelled out. So we get 12 into 10 raised to power minus 7 Tesla. So that is the magnetic field produced by one of the side. How many sides we have? 6 sides. So you have to multiply 12 into 10 raised to power minus 7 with 6. You will get 72. So 72 times, so x will be 72. Right? So 72 is the answer. 72 times 10 raised to power minus 7 Tesla. Again, this is the same question, but instead of a regular hexagon, we have a square. By using the same logic, we can find the answer of this question also. So I'm keeping this question as a homework for you. You can try this. The answer is 40. Now let us see the next concept, a semicircular wire. So here we have, suppose if we have given a wire which is not semicircular, suppose it subtends some angle theta at the center. So there is a wire which is having a current I, and it subtends an angle theta at the center, right? So first of all, what is the magnetic field at the center? You can curl your fingers in the direction of the current. Thumb will give you the direction of magnetic field, so it comes out to be into the plane. Since the current is clockwise, magnetic field will be into the plane, so it will be cross. And this magnetic field will be mu naught I upon 2r, r is the radius, times theta upon 2 pi. So this comes out to be mu naught I upon 4 pi r times theta. So this formula you can remember. And if you want to find the magnetic field by a semicircular wire, theta will become pi. Right? So if we have a semicircular wire, theta is pi. So this comes out to be mu naught I upon 4r. And if you want to find the magnetic field via the complete loop, in that case theta will become 2 pi, and the answer comes out to be mu naught I by 2r. So let us see the question. The magnetic field at the center of a wire loop formed by two semicircular wires of radii r1 and r2. R1 is 2 pi meters, r2 is 4 pi meters, carrying current I, which is 4 ampere as shown in the figure, is alpha times 10 raised to power minus 7. So the magnetic field at O is 10 raised to power alpha times 10 raised to power minus 7 Tesla. We have to find the value of alpha, right? So what you can say, there are four segments, right? So we have two semicircles and two straight segments. So this one and this one, right? So let us say the current is in clockwise direction. So if you consider these straight segments, can you see this point O? If I extend these straight segment, this point O lies on that particular line. So what you have to remember, in this case, for 1 and for 2, the magnetic field will be, there will be no contribution towards magnetic field by 1 and 2 sections. So we have to consider only semicircular loop. Why? I told you the formula for finite wire, it was mu naught I upon 4 pi d times cos alpha 1 minus cos alpha 2. So here alpha 1 and alpha 2 are both 0 or 180. So that will so the field due to 1 and 2 will be 0 at O. So you don't have to consider the flat section, right? So we are left with only semicircular wire, and if you consider the bigger semicircle, again if you curl your fingers in the direction of the current, thumb is pointing into the plane. Similarly, for small semicircle, it is again clockwise, the thumb is pointing into the plane. Again, we are getting into the plane, so you have to add both the fields. So we can say the magnetic field produced by the bigger semicircle will be mu naught I upon 4r2 plus mu naught I upon 4r1 due to smaller semicircle. So from this, mu naught I by 4 will be common. So 1 by r1 plus 1 by r2, which will be 2 pi and 4 pi. So let us put the values. So it will be 4 pi times current is 4 ampere divided by 4, and this will be 3 by 4 pi. So 4 pi will get cancelled out, and we have 10 raised to power minus 7 also. 4 will get cancelled out, so it will be 3 into 10 raised to power minus 7. So that should be the answer, right? Alpha will be 3. Now let us see the next concept, circular wire at its center. So magnetic field due to a circular wire at its center, and we have just discussed that if there is a circular wire which is having a current I, radius is R, you have to curl your fingers in the direction of the current, thumb will give you the direction towards you, out of the plane. So magnetic field is out of the plane and radius is R, so it will be mu naught I divided by 2R. So that you have to remember. And suppose if you want to find the magnetic field at a point on the axis, let me also show here also. So if there is a circular coil and we want to find the magnetic field at a distance x from the center of the coil, and let's say it has a current in this direction. Now if you curl your fingers in the direction of the current, thumb is pointing in the right direction. So in this case the magnetic field will be in the right direction. Let us say R is the radius, current is I, radius is R. So it will be mu naught I R square, let us say capital N is the number of turns, divided by 2 x square plus R square raised to power 3 by 2. So this formula you can remember, and this N is a natural number, right? It can't be a fraction. Got it? Right, so let us see the question. A circular, two circular coils P and Q of 100 turns each have same radius of pi centimeter. The current in P and Q, P and R are 1 ampere and 2 ampere respectively. P and Q are placed with their plane mutually perpendicular with their centers coincide. The resultant magnetic field induction at the center of the coils is root x milli Tesla. We have to find the value of x, and mu naught is given as 4 pi into 10 raised to power minus 7 Tesla meter ampere inverse. Right, so let me first draw the diagram here. So we have given two perpendicular coils, right? Let us say this is x-axis, this is y-axis, and this is z-axis. and there is a red coil which lies in XY plane, right? And let us say it has a current in this direction. So if you curl your fingers in the direction of the current, thumb is pointing in the upward direction. So we can say the magnetic field will be in this direction. This will be B1. So this is the coil P, right? Now if the coil Q is perpendicular to this. So let us say the coil Q lies in XZ plane and they have same radius, right? So it can be shown like this. And let us say it has a current in this direction. So if we curl our fingers in the direction of the current, thumb is pointing in the positive Y direction. So that will be B2. So can you see B1 and B2 are mutually perpendicular to each other? Since they are perpendicular and we want to find the net field at the center because their centers are coinciding, na? So the field should be vector addition of these two vectors. So we can say the B net field will be root of B1 square plus B2 square. Now what is B1 here? So B1 is the magnetic field produced by the coil P. Coil P has 100 turns. So we can say 100 times mu naught times the current, which is 1 ampere, divided by 2R, and R is pi centimeter, so 10 raised power minus 2. Right, so what is B2? So B2 will be number of turns, which is 100, times mu naught times the current, which is 2 ampere, divided by 2R, 2 times pi into 10 raised to power minus 2. Okay, so if you look at these two field, this 100 pi 100 mu naught and the denominator, both these are common, right, in both the fields. So we can say it will be 100 mu naught divided by 2 pi into 10 raised to power minus 2 root of 1 square plus 2 square. So this comes out to be root 5. Okay, so let me further solve this. So we can say 100 times 4 pi times 10 raised to power minus 7 divided by 2 pi into 10 raised to power minus 2 times root 5. So let us simplify this. So this will give us 2. So it will be 2 into 10 raised to power, it will be 4 minus 7, so minus 3 root 5. And if you look at the question here, they have given it is root x millitesla. So we can say this is milli. So we can say it is 2 root 5 millitesla. So it means this 2 root 5 is root x. So root x is equals to 2 root 5. So x will be 4 times 5. So it comes out to be 20. So 20 is the answer of this question. Right. So I hope this concept is clear. And again, it is the same question which I'm keeping as a homework for you. You have to use the same concept, same logic, and you have to use this formula B1 square plus B2 square. So the answer of this question is option 3. Just try to solve this, you'll get this answer. The next concept is infinite wire. So if we have a infinite wire, let me show you. First, let me take a case of semi-infinite wire. So this is a semi-infinite wire. One end is not visible to us, one end is visible, right? And we want to find the magnetic field at point P. And this distance is D, let us say. So the current is in this direction. So if you again use right hand curl rule, current is coming, field will be at P, will be out of the plane. So field will be out of the plane and the magnetic field will be given as mu naught I is the current, divided by 4 pi d. But what is a infinite wire? So let us say this is a wire, both ends are not visible to us, they are quite far from us, right? And current is in the right direction. We want to find the field at point P, which is at a perpendicular distance d. So in this case it will be mu naught I upon 2 pi d. Okay, so this you have to remember, and the field will be out of the plane. Right, so let us see the application of this. Two long straight wires carrying equal currents in opposite direction are shown in the figure. The separation between the wire is 5 centimeter. So this distance is given as 5 centimeter. The magnitude of the magnetic field at the point P midway between the wire is dash microtesla. So we have to find the magnetic field at point P. Okay, so if you consider left wire, which is an infinite wire, the magnetic field at P will be into the plane, and due to the right wire, the magnetic field at P will be into the plane. So both the fields are getting added up. So and by symmetry, we can say both the wire will be having same magnitude of field. So let us find the field by one of the wire, and then we'll double that. So it comes out to be mu naught I upon 2 pi d times 2. So that what we have to do. So d will be 5 by 2 centimeters. So it comes out to be 4 pi into 10 raised power minus 7. Current is 10 ampere divided by 2 pi. Okay, right. So let me eliminate this 2, right? So 2 will won't be there. D is 2 point, or we can say 5 by 2 centimeter, 10 raised power minus 2. Okay, so this pi will get cancelled out and this will give us 2. So we got 4 times 4, that will be 16 times 10 raised power minus 5, and we have to find answer in microtesla. So it comes out to be 160 into 10 raised power minus 6 Tesla. So which will be 160 microtesla. So 160 is the answer of this question. Next is semi-infinite wire, which I have already discussed. The magnetic field will be mu naught I upon 4 pi d. Let us see the application of this. Right, sorry, answer is already given here. So let us calculate this. A hairpin like shape as shown in the figure is made by bending a long current carrying wire. What is the magnitude of the magnetic field at the point P, which lies on the center of the semicircle? Okay, right. So here we have 3 segments. There are 2 semi-infinite wire. Let me call this as 1. And there is another semi-infinite wire. This is 2. And there is a semicircular wire. This is 3. So we have to find field by individual segments, and then we have to vectorally add the fields. Now due to segment 1, the magnetic field at the center will be into the plane, and due to segment 2 it is again into the plane, and due to the semicircular wire it is again into the plane. By curling your fingers in the direction of the current, it is into the plane, right? So all the 3 fields are getting added up because they are pointing in the same direction. So we can say B1 is equals to B3 or B2, and it is equals to mu naught I divided by 4 pi small r, and B3 is mu naught I divided by 4r. So we have to add B1, B2 and B3. So this will become 2 times mu naught I upon 4 pi r plus mu naught I by 4r. So mu naught I by 4r will be common. And if you look at the option, everywhere they have taken r common, right? And pi also common. So let us take pi common. So let me multiply and divide with pi. So 4 pi r, and pi is also common. So this will become 2 plus pi. So pi plus 2 times mu naught I upon 4 pi r. So option 2 is the right answer. Next concept is Ampere's circuital law. So let us see what is this law. If we have given some loop, right, and there are certain current which is piercing this loop, I1 is there, I2 is there, right? This is I3, and there are certain current which are not piercing. This is I4, this is I5, right? So according to Ampere's circuital law, if we take a line integral of magnetic field on this closed loop, let us take the direction. We are taking a small element dl. So the closed integral of B dot dl will be equals to mu naught times the net current which is piercing the loop. Now what should be the direction of the current which we have to take positive? So if you consider I1 is in the downward direction. If you curl your fingers it is opposite to the dl vector, right? Because dl vector is going like this, right? Anti-clockwise sort of. If you look at it from the top, it is anti-clockwise, and the current I1 is going into the plane if you look at it from the top, right? So if I point my thumb in the direction of I1, fingers are curling in the clockwise direction, but the integration is happening in the counterclockwise direction, so I1 will be negative. Similarly, I2 will be negative and I3 will be positive. So it comes out to be mu naught times minus I1 minus I2 plus I3. Okay, so if you look at this equation, the left hand side is the magnetic field produced by all the sources available, whether they are piercing the loop or not piercing the loop. So B is due to all these 5 currents, but on the right hand side we have to take only the currents which are piercing the loop. So by using Ampere's circuital law, we can find magnetic field by symmetrical current distribution, like the infinite long wire. We can find magnetic field by that, or a solid, you can say a solid infinite cylinder or hollow infinite cylinder, we can find magnetic field. Now let us see one of the application of Ampere's circuital law. In a coaxial straight cable, the central conductor and the outer conductors carry equal current in opposite directions. The magnetic field is zero, so we have to find at which place the magnetic field is zero. So here we are going to use Ampere's circuital law. Let us see. So we have given a coaxial cable. So this is the core and this is the outer conductor. Okay. At in the core, let us say the current is out of the plane, and the total current is I. And for the outer conductor, the current is into the plane, let us say. This is the cross-sectional view, right? And this current is also I. So if I consider by symmetry, if I consider an Amperian loop, right, and the center of this loop lies on the axis of the cable. Let us say the radius is r. If so, for this Amperian loop, the net current which is piercing will be zero. Why zero? If I consider counterclockwise as the direction of integration, so by symmetry, so we can say integral b dot dl. It can be written as b times 2 pi r, and the right hand side will be mu naught times. So we can say the current in the core will be positive and the current which is in the outer conductor will be negative. So it will be plus I minus I. So it comes out to be 0. So there is no net current is piercing the Amperian loop. So integral b dot dl will be 0. So b comes out to be 0. So if you consider any Amperian loop which is outside, the magnetic field will be 0. So we can say outside the cable, the magnetic field will be 0. So option 1 is the right answer. Now let us see the next concept, and it is based on the magnetic field produced by an infinite solid cylinder which is having a uniform current density. So I'm showing the cross-sectional view. So let us say there is a infinite solid cylinder and it is having the current density out of the plane. So the current is out of the plane and its radius is capital R. So the radius of the cross section is capital R, and we want to find the magnetic field inside as well as outside. So if I want to find the field, let us say at a distance R from the center. Okay, so inside, magnetic field is given as mu naught by 2 J cross R. So if I want to find the field at this particular point, this will be the R vector, which is from center to that particular point, and J vector is out of the plane. So the magnetic field, if you apply J cross R, it comes out to be downward. So the magnetic field will be in this direction, right? Because J is out of the plane. Outside, if I want to find the field, let us say at a point, at this particular point, where R vector is R. So again, so here the magnetic field will be perpendicular to R vector. So outside, magnetic field will be given as mu naught times the total current, which will be J times pi capital R square, divided by 2 pi small r. Right, so this formula you can use, or you can directly write it as mu naught I upon 2 pi r. Okay, if you know the current. Right, so whatever formulas that we are discussing, you should also know how what is the graph for magnetic field with respect to the distance from the center. So that can also be asked in JEE Mains. Let us see one of the illustration based on the same concept. A long straight wire of radius A carries a steady current I. The current is uniformly distributed across its cross section. The ratio of the magnetic field at A by 2 and 2A from the axis. So here we're given a wire which is having a cross-sectional radius A. So this is A. Let us the current is out of the plane. So total current is given as I. And we want to find the magnetic field inside as well as outside. Say point A and point B, and the center is O. OA is given as A by 2 and OB is given as 2A. So this is inside and this point is outside. So we know that the formula is not same for inside and outside. So if I want to find the field inside, so magnetic field at A will be mu naught by 2 J cross R. So it will be J will be current divided by the area of cross section, pi A square. So that is J. And what is R? R is OA. OA is A by 2. So this is BA, and magnetic field at B will be mu naught times I divided by 2 pi times R. R is OB, that will be 2 times A. So let us simplify this. So this will be mu naught I upon 4 pi A. This is mu naught I upon 4 pi A. So if you look at these two relations or these two magnetic field, they comes out to be same. They have same magnitude. So the answer is option 2, which is 1:1. So we have to find the ratio. Right, so let us see another illustration. A long straight wire of cross-sectional radius A is carrying a steady current I. So I'm assuming this current is uniformly distributed. The current I, and it is also given, right, uniformly distributed across this cross section. The magnetic field, so we have to find how the magnetic field is varying with respect to the distance from the center. So if you look at the formula, outside, inside, magnetic field magnitude will be mu naught times J times R divided by 2. So it is directly proportional. So B is proportional to R, and outside magnetic field is mu naught I upon 2 pi R. So here B is inversely proportional to R. So if you look at the option 3, it says the directly proportional to R in the region less than A and inversely proportional to R in the region greater than A. So option 3 is the right answer. Right, so the next concept is solenoid. So in case of an ideal solenoid, the magnetic field, okay, let me just show you. Suppose there is a cylindrical core and there is a wire which we have wound over this cylindrical core. Okay, and let's say there is some current. Now the length of this solenoid is very large in comparison to the radius of the area of cross section. So when that is the case, when L is very large in comparison to R, we can say the solenoid is ideal. And in case of an ideal solenoid, the magnetic field inside the core is uniform, right? So if I show the magnetic, if you curl your fingers in the direction of the current, thumb will give you the direction of the magnetic field. So in this case, the magnetic field will be in the right direction. So in case of a ideal solenoid, somewhere in between, at the center, you can say the magnetic field at the center will be mu naught times I times n, where small n is the number of turns per unit length. Small n is the capital N is the total number of turns in the solenoid, L is the length of the solenoid. And at the ends, so this is the end. So at the end, the magnetic field is given as mu naught I n by 2. So it will decrease. It becomes half at the end. So that you have to remember. Let us see a question. A solenoid of length 0.5 meter has a radius 1 centimeter and it is made up of m number of turns. It carries a current of 5 ampere. If the magnitude of the magnetic field inside the solenoid is 6.28 into 10 raised per minus 3 Tesla, then the value of m. So we have given magnetic field and we know the formula. It will be mu naught I n. So here it will be mu naught I n is nothing but small m divided by the length, and length is given as 0.5, right? So let us put the values. We have to find the value of m. So m will be bl divided by mu naught times I. So b is 6.28 is nothing but 2 pi. So 2 pi into 10 raised per minus 3 is the magnetic field. Length is 0.5. Mu naught is 4 pi into 10 raised per minus 7. And the current is 5 ampere. So let us simplify this. So this will give us 2 and 2 and 5 will be 10. So it comes out to be 5 into 10 raised per minus 4 plus 7 minus 1. So it will be 500. So 500 is the answer. Okay. Now here we have done similar cases, right? So we have given 4 different arrangements and we have to find the magnetic field at O. So I'm keeping this as a homework. You can try this and check whether you're getting 3 as the answer or not, right? So 3 is the answer of this question. So do practice based on the concept that we have discussed so far.